Okay, so it is a pleasure today to introduce Dr. Neha Patankar, who got her bachelor's degree at, and Neha, correct me if I'm pronouncing this incorrectly, but Savitribai Phule University. Okay, good enough, close enough. And
Good enough.
okay, thank you. That's kind of you, I'm sure. Her doctoral degree at North Carolina State University. Um, she is an assistant professor at the School of System Science and Industrial Engineering, and she is going to be sharing her research with us on energy transition and how that research can support decision-making on renewable energy deployment and ensuring a clean and resilient energy grid. And pass it on to you, Neha.
All right. Thank you for the introduction. I'm going to share my screen. Let me know if it is proper.
I'm wondering if my wish to see people's faces is leading to audio problems or bandwidth problems. Are you getting that on your end, Neha? I'm getting some garbling.
Yeah, a little bit.
Okay. All right. Well, then let's go. Sorry to do this, Neha. I'm happy to stay on with the video, but
Not a problem.
Okay. All right.
All right. I'm keeping my video on just for now, but if we get more disturbances, then I'll turn it off. Okay. All right. Hello, everybody. My name is Neha Patankar. Thank you, Juliet, for the introduction. I am going to keep this pretty informal, this presentation, because this is something that I have realized that talking through the methodologies and just discussing it with students and collaborators, it's good to generate ideas. So if you have any questions or if you have any doubts about how a particular thing was created or formulated or solved, just feel free to interrupt me in the middle and ask your questions. All right. So for today, I'm going to talk about a general broader topic about how to make collaborative decisions on the way to net zero energy systems. And I'm going to talk specifically about electricity sector. All right. So I'm going to start with this figure, and I'm pretty sure you all are pretty familiar with these projections. They are from the IPCC 2018 report, and they basically show how much CO2 we are emitting as a globe and where we need to go 30 years, in 30 to 40 years. And we are right now in 2025 already, so we are less than 25 years away from the 2050 goal. And within our lifetime, we want to achieve this net zero target or below zero target. And that's a pretty ambitious goal. But because of this goal, and because of the requirement for this goal, know that many parts of our energy systems are going to change in the US energy system. So these are your primary energy sources. It's being converted into secondary energy sources like electricity, and then it's converted into final energy demand, such as the light we get in our houses, or heating, or cooling, or our transportation demand, etc. And the point is that this entire flow is very complex, and this entire flow is in the process of transition to a more cleaner flow of energy. Now, especially in this entire flow, we expect that in our early careers or in the next 10 years or so, the electric sector in particular to change the impact of Inflation Reduction Act. And as you can see, this is how much US generated in terms of capacity from 1950 to 2020. There was a coal boom here. This was 2000s, the natural gas boom, the shale gas. And now we are kind of standing in, we expect to see unprecedented amount of solar and wind growth over the next over the next decade or so. And because of this unprecedented growth, we know that we're going to be a lot of jobs. So we have already started facing some of them. There is an ecological trade-off. There is a trade-off between air quality and water quality. We just saw a couple of years back what happened in Texas with the snowstorm. So there is a trade-off between how much people are willing to pay to weatherize the electricity infrastructure versus versus what happens if we don't weatherize. And essentially, we are going to see a lot of these type of trade-offs going forward. So we really need to understand these technological, social, and environmental trade-offs well. That's associated with long-term energy transition. And so what I do in my research is I use optimization-based models to consider different objectives of different stakeholders and try to figure out robust technology deployment pathways. So in general, I use socio-techno-economic systems that has 3 layers. The first one is the engineering layer. So we need to know how the power plants function. We need to know how end-use energy devices like electric vehicles or heat pumps function. We need to understand how pipelines work, transmission lines work. We then need to know the economic and behavioral layer. So we need to understand how technology cost is going to change, what fuel price will be like a few years down the line, what are different preferences and priorities of different actors in the system. And the third one is the regulatory and policy layer. So this is where we need to model the top-down economic regulations. We need to create market designs. We need to be able to model different market designs or different energy and environmental policies. So to consider all 3 of these layers, we have essentially created an end-to-end modeling pipeline that takes into account a very, very detailed input data set and try to understand different local, technological, social, environmental trade-offs in a better way. So this modeling framework is kind of broken down into 3 layers. And the first one is the traditional capacity expansion models. So there are 2 types of them. One is focused on the entire energy system. There you consider the electricity part of it, but also the commercial sector, and look at the entire flow of energy through the system. And I worked on it quite a bit over the last decade, but recently I have moved a little bit more focus on a power sector, especially because that is the sector that's expected to change the most. So I have co-developed a model called GenX with colleagues at Princeton and MIT. It's built in Julia and Jump, it's open source. And it has 3 dimensions, 3 major dimensions. The first one is a network dimension, second one is a temporal, and the third one is operational dimension. And in each of these dimensions, you can essentially change or increase or decrease the complexity of the model, depending on what question you would like to answer. In general, we use a zonal model. So if you're modeling, let's say, the Eastern Interconnect, the eastern part of the United States, you could model different parts of that interconnect as separate zones. We usually model representative hours or representative time periods. And we use unit commitment and reserves with linear relaxation or linearly relaxed constraints. And For the type of problem that we are looking at to see how power system would progress over the next 10 years or so, this model resolution helps us understand that question in the best possible way. But you can think of it like a Swiss Army knife, where you can use one tool at a time or increase one complexity at a time. But you have to kind of figure out there is a trade-off between the complexity and in one dimension with the complexity in the other dimension. All right. So now this first one is essentially a bunch of equations in a code, right? And here there is an objective function. It's an optimization model. So it's a cost minimization objective function. And there are many different parts of this cost, such as investment cost, variable cost, transmission expansion cost, cost of energy that is not served, startup shutdown cost related to. And then there are all this model. We get to learn 5 different things. When and where to invest in generation capacity. Second, we know how to dispatch and operate that capacity. Third, we know how and which demand segments we should serve, which we might want to curtail. Fourth, we learn how to commit and cycle our thermal units. And lastly, we learn when and where to invest in transmission infrastructure. So now, as I said before, this model is just a bunch of equations. And to really make them work for us, we need to have much more, we need to have GIS layers that tell you where you can't physically build the infrastructure, renewable infrastructure or transmission infrastructure. So you think about national forests, state forests, built infrastructure, roadways, waterways, military infrastructure, aviation infrastructure, or any such land where you can't physically build that structure. So there are 60 such layers. And for the remaining land, it's not very visible here, but we kind of break down the remaining land into 4 by 4 kilometer square candidate project areas. So let's say there is a candidate project area somewhere in Montana. We have generated a transmission cost surface data that allows you to find the cost of transmitting electricity from that site to where it is actually needed, right? So Montana has a very low population, so you might not want to build a bunch of PV in there because you will have to consider the cost of sending that electricity from Montana to maybe Denver, right down in Colorado, of that generation seat. Now, we put all of that detailed information of site suitability into a tool that I have also co-developed, which is called Power Genome. And Power Genome is essentially a quick and easy way to create input data set for any region in US. It also takes into account the other power system related data, like what are the existing generators, the transmission constraints, state policies, load profiles, renewable generation profiles, cost projections, or anything else that you need to build a power system model. It puts it into an energy system model or power system model at a spatially aggregated resolution. Here I'm just showing one of that aggregation. And then for your policy, we lease model to achieve that. Once we have the capacity expansion results for, let's say, 2030, we kind of maintain the linkage between that very, very detailed data and that aggregated data or aggregated results and use it to map it back to their original resolution. It's a little difficult to see on this figure, but you can see that the dark blue ones are existing infrastructure for wind. Light blue ones are the proposed ones. There are transmission lines. There is this particular transmission line from Minnesota down to Chicago, which is pretty prominent. And you can see how exactly that renewable or transmission infrastructure might need to change to achieve that policy goal. And so once we have this result, we can look at many different impacts of that development. We have mainly looked at land cover and land use impact for now, but you could look at employment impact, water quality impact, air quality impact, or different trade-offs such as prime farmland versus forest land versus land used for PV development, etc. And now this was our second layer, right? But here we realize that this solution is just what the model is telling us to do, and it's just one solution. What happens on ground is usually going to be much different than what the model is showing us, because there are many on-ground objectives that the modeler, one single modeler or one single model cannot consider. Here, this is just one solution, that is least cost solution for New York State. For the rest of the presentation, I'll be focusing specifically on the New York State, just because that's what we are working on right now. And as you can see, it basically says that to achieve the 70% renewable portfolio standard target by 2030, the model is telling us to not build any new wind, right? The onshore wind is, you don't see onshore wind in here, maybe just one in here. And it's asking us to solely rely on PV. And as you would, one would say that that's not exactly what's going to happen, because there are onshore wind farms that are being proposed at the moment as well. So again, this is just one solution that the model is telling us to do based on the techno-economic assumptions we have provided it to. So we learned that, or we understood that to understand trade-offs in long-term energy system model, if we do not know the objectives of the stakeholders, and if we still need a planning strategy, then we need to use a methodology called modeling to generate alternatives. So in general, what this method does is it sequentially finds maximally different technology pathways. So let's say that this is your feasible space. On x-axis, you have PV capacity. On y-axis, you have wind capacity. And this space here represents combinations of PV and wind capacity that are feasible for your problem. And let's say that this dot over here is your optimal combination based just on cost. So what we do is we tell our model that, okay, let's say this solution costs you $100, right? Let's say you have $110 in your pocket. So we create something called a budget constraint. And we ask the model to tell us all of these extreme points, which are other combinations of these technologies that are feasible and near cost optimal, right? And this solution in here might satisfy some stakeholder objective that this particular solution in here might not. All right. So let's say this is your optimization problem. Minimize C transpose X, subject to X equal to B. Let's say X1 is your optimal solution for the original problem. The idea is to maximize the absolute distance between a new solution and the previous solution, such that your new cost is within the previous cost plus some slack. That's plus some relaxation in your budget. And we kind of continually keep on doing so. Now this looks deceptively simple, but when you have absolute value in the objective function, you need to have creative ways to get past it. I'm not going to go too much into the details about what we did to get past it, but if you have questions, I'll be happy to talk about it. All right. So solving the problem like this essentially gives us this new solutions, which are these red dots, near cost optimal solutions. Now, we have tested against several methodologies. There is a heuristic that works well for larger problems. Again, if you have questions, I'll be happy to talk about it. Okay. So now coming back to the New York state model, let's say you are a stakeholder, right? Let's say you are a grid operator. So your objective might be to enhance grid flexibility and reliability, right? Maybe you are a state regulator and you really want to push for that 100% renewable grid. Or maybe you are a utility company and you want to lower the grid congestion and you want to lower the peak demand costs. Or maybe you are an environmental and community groups and you want to really reduce the fossil fuel peaker plants that are near New York City and its reliance on the EJ communities. Or maybe you are a renewable developer and you want to improve the energy market efficiency and you want to maximize your revenues from your solar farms or wind farms. Or you are a consumer like you and I, and we really want to make sure that our bills don't shoot up and we have reliable electricity supply at all times. And so these are many different stakeholder objectives that we can potentially convert into a proxy objective, such as if we can maximize the usage of battery technology in the state, it helps us satisfy or work towards majority of these goals. So let's say we create 200, so for this particular problem, we created 200 near cost optimal solutions that look very different in terms of technology portfolios within the 10% budget of your lease system cost. So one of the proxy objectives we looked at was to maximize battery capacity in state. And we wanted to see, okay, within the 10% budget, if your goal was to just really, really push for battery capacity, how far can you push? And what would be the effect of that policy on the rest of the technology portfolio? And so one solution here we see is that now we have much more wind in the system, especially concentrated in the West. And so majority of the battery capacity is also concentrated in the West. And again, this is just one solution, right? And New York has a 6 gigawatt battery capacity goal. And in the least cost solution, you don't build anything more than 6 gigawatt. But in this case, within that 10% budget, we are able to build much more battery capacity in state while achieving the 70% goal and while keeping your cost reasonable. Now, we could have many such alternate portfolios, right? That can be our proxy objectives. We could have minimization of high voltage interregional transmission lines. They tend to face a lot of backlash. or we might want to maximize the utilization of flexible demand resources. And essentially, these objectives allow us to visualize the decision space that does not break our budget. So here I'm just showing one example. If you see, apologies for the poor quality of this figure, but here we have the solar versus onshore wind capacity. This one is specifically assuming low renewable cost projections, so optimistic renewable cost projections and high electrification demand scenario. And we see that they are, of course, negatively correlated. And we see the combinations of solar and wind capacity that can satisfy our goal. And this is, again, we can use a similar methodology to figure out your decision space that is also robust to all of these other uncertainties about renewable costs or electrification levels. So there are 3 such decision spaces here. And if you overlap it, we can essentially see that this portion over here, that is this combination of solar and wind capacity, are feasible, cost optimal, and work well under different realizations of these uncertainties. Now, we realize that these are lots of different combinations of technology portfolios. And it's very hard to communicate these trade-offs when you have so much data for data that you're producing. So we created something called a community energy compass. It's essentially a tool that you can use to foresee energy trade-offs. And you can basically facilitate a better communication of that trade-off and for collaborative energy transition. I'm just going to give a small demo for this tool, and we will go to the Q&A then. All right. So this here, it's not published yet, so I would appreciate any feedback that you might have. All right, so this first tab shows you 200 different combinations. So the dots over here, you can pick any of this dot, and that you the technology portfolio looks like. These are the same regions. Thus here pushes for wind capacity to increase. And if you remember, the least cost solution hardly have had any wind in the system, but now wind shows up quite a bit just within that 10% budget. We can go a little bit ahead, zoom in this figure. And let's say we select this particular solar farm in the near Rochester. You will have a CPA ID here. This is the candidate project area ID. You can enter the ID in here and download a CSV file that tells you a lot of information about that particular site, about whether it is, how close it is to road infrastructure or substations or transmission lines, what's the population density in there, what type of land it is, what's the area of that site, what type of land cover it might have, or whether maybe we can go a little bit further and we can get additional information about ownership of land for that site. So this is just a CSV that you will be able to download. It tells you who owns that land by acre. I have, this is just in a decreasing order, so you know that if a renewable developer wants to develop that site, then majority of that site is owned by a particular person or an entity or an organization, and we can essentially prioritize how we go about the development. All right. There is this part in here, which is adjustable scroll bars. And if you are a stakeholder who might not really want large wind farms in their backyard, right? So you might want to see, okay, we want to reduce onshore wind capacity. We don't want too much of it in the system. What's the impact of that objective on the rest of the solutions space? So you can see that your solutions look down. Your solution is kind of, it's no longer okay to build very low amount of solar. You have to build quite a bit of solar to achieve low amount of wind in the system. Similarly with natural gas or offshore wind, etc. You can scroll a little bit down, and for that particular solution, you can see where the investment will be going in different regions of New York. So it says that a lot of investment is going in this western part. A lot of investment is going in this northern eastern part. And that helps communities to also decide how the investment is being spread out. As well as on the right-hand side, you can see how the emissions are being spread out. That's tab number 1. We can go a little bit more detail and see, this is again zoomed in near the northern part of New York. We can see all of the potential cost-effective sites, right? So each site here appears in at least one portfolio. And let's say you have this site in here. That's very near to this forest and might have it that we ahead of time. So on the rest of the system. So as you can see, these highlighted sites have disappeared from your solution space as well, due to the transmission infrastructure or due to the way the solution is structured. That was the second tab. The third tab shows you the trade-off between different attributes. So technology capacity is just one proxy attribute that we are using, but there could be other attributes that are more relatable for communities, such as employment or land use. And in here, you see the decision space between natural capacity and solar capacity, and how much minimum and maximum solar you can build. And let's say you want to maximize solar for that amount of, you can see how it would impact the land use in the area. So this is the natural gas versus land use plot. And down here, you can see for that particular solution, you can see the natural gas, battery, or other technology capacity. We have other attributes in here, as I said before. You can choose, we are still populating it. This is still work in progress. So you can choose one or more of them. We can also do the same thing at a regional level. So if you are focused on the Cornell or Binghamton area, which is the central part near the Finger Lakes region, then you can also see the trade-off for that particular region. And the last one is we realize that two stakeholders might have their objectives and might want to create a new solution that considers both of their objectives. So for now, we have considered only the investment in different regions and the emission in different regions. And let's say this region number 4 is, they're saying that we don't want too much renewables in our area. It's a very beautiful, gorgeous landscape, and we don't want uh, we want to kind of preserve it the way it is. So if you want solutions, provide the weightage for those solutions and create a new solution, which we can create because of the convexity of our decision space. And we can see that in that particular region, our investments have significantly reduced. We can also then downscale that solution in here and see how that particular solution looks like on ground if you downscale it. Now, there are many different limitations on this. This is also, again, work in progress. But there is a little bit lack of realism right now in here because our transmission constraints or data is quite simplified. And we might have some unrealistic system feasibility. We do have bidding Gs, and so we are ignoring grid bottlenecks. We are not exactly considering the battery cycling, and we do not model the grid resilience under extreme conditions. However, to kind of get over these limitations, we are actively working with a team in Cornell where they have the operational model, we have the capacity expansion model, and we are working on connecting both of them to make sure which of our portfolios satisfy the operational constraints and can also have a optimal, cost-effective solution. I'm going to stop there, and I'll be very happy to answer any questions. Thank you.
Great, thank you so much. Neha's really great presentation. And if you could join me in giving Neha, Dr. Patankar, a virtual round of applause. Thank you. And yeah, we'll dive into some questions. What do people have? I can maybe kick us off. So I feel like there's so much to dig into here and exciting and really helpful to see you share that work. If you have a question, if you could drop it in the chat. I think one of the things that I'm wondering about is how you're dealing with some more distributed technologies like rooftop PV as opposed to utility.
Yeah.
And also dealing with some emerging technologies or sort of new configurations of old technologies. And in particular, here in Massachusetts, we're thinking a lot about network geothermal systems as a possible route to increase efficiency of heating, and especially with electrification. And then of course there are like energy efficiency incentives for buildings and potentially, increased use of mode shift in transportation. So I'm just curious how you deal with all of those different issues.
Yeah, that's a lot of questions. I'll go one by one. So first one, the distributed technologies like rooftop solar PV. We get projections from NREL. They have the Cambium data set, and they have projections for all states pretty much for what the rooftop PV capacity would look like till 2050, right? So there are ways we use it. One, we direct projection or not cost effective, so it does not show up in the least cost solution. But the idea is it might show up in a near cost optimal solution, right? So we use that rooftop solar PV base projections from Cambium, and then allow for the MGA, the alternate portfolios, to choose rooftop solar PV in their near cost optimal strategy. So it works both ways. So you have the base, plus you have a possibility of building more if it is within budget. Second one is about the upcoming technologies like geothermal. That's something that we have not considered right now, but you can essentially put the cost projections, the efficiency projections in there. And we do have little bit geothermal right now. Model does not build as much, but more advanced geothermal is something that we need to put in the model, and we haven't done that yet. Hold on, what was the third question? The electrification, is that so? Yeah. So electrification demand projections we also get from NREL, National Renewable Energy Lab. They have a base demand projection, and then they have vehicle stocks, electric heat pump stocks, and we adjust them based on our projections from the Inflation Reduction Act study. That one is a energy system model. So there you have the demand for heat pumps, demand for electric vehicles as a variable. So you have again the base projections from NREL, and because of IRA, you might have some more EV or heat pumps in the system. So you use that stock as an input parameter, create a new profile for electrification, and put that electrification profile in here. So in this model, in the GenX model, or in the tool that I showed you, electrification is fixed, or the electrification profile is fixed, but we kind of do a pre-processing on that to consider the impact of policies that are proposed or that are enacted. Okay, I answered 3 questions. Did I miss something?
I want to make sure students no, that's great. I want to make sure students have a chance to ask their questions. So we'll pass it over to the chat. Looks like Walter has a question. So in the future, the hope is that the model will take grid bottlenecks and energy storage capacity into account.
Yes. So right now, our energy storage capacity, we have a possibility to build anything between 1 to 10 hour storage. And the model decides how big of a storage or in terms of energy capacity it wants to build. It also considers the bottlenecks in terms of inter-regional transmission lines. So there is a representation of Western New York or Central New York, and there is a transmission line that connects both of them. But that's not exactly how the transmission is working on ground. So we consider bottlenecks, but not as realistic as it should be. In the future, in our project that's ongoing with Cornell, we want to kind of take this downscaling results, put it into their model, which is much more detailed transmission model, and see how the storage operates and how the grid bottlenecks show up. Yep.
Okay, we've got another question, which is, will this impact further on ongoing resource conflicts for things like water rights or hydro?
Yeah.
Brian.
Yeah, thanks for that question. Yes, so there is this transmission line from Hydro-Quebec down to New York City, which has received a lot of backlash over the last 4 or 5 years. And that has to do with water rights or the ecologically important landscape around the river. And yes, this tool can essentially say that, okay, if this part of the transmission line is facing a lot of backlash, or if this particular transmission line cannot be built further, then what is your alternative? And is that alternative possible within your budget? Or if you don't build that line, there's just no possible alternative without blowing your budget. So those type of questions, yes, we can answer. For water rights, we can. So there are also wetlands that sometimes come up as a new potential wetlands because of the changing climate landscape. For example, there is a new wetland categorization near Binghamton, which was a dry wetland for years, but now it is considered as a non-dry wetland. And so, yeah, those type of things that help us kind of deselect that site if that is something we haven't considered ahead of time.
Looks like there's one more question from Walter. Was there anything you personally or your team found interesting about the data during your research? Anything that was against your initial expectations? It's a good question. Prizes.
Oh, wow. Yeah. Yeah, thank you for that question. There are so many things that were, oh, wow moment. The first thing, I mean, this is that first observation is what kickstarted this entire project, was that for decades almost, capacity expansion model were just least cost models, right? Majority of the capacity expansion models used by many governmental agencies or national labs, even now, predominantly depend on least cost portfolios. And when we added this 10% budget, we were completely blown away by how flexible the system could be in terms of technology portfolios. Yeah, that was something that we were not expecting. Just a little budget. There are so many knife edge solutions, and we realized that it's not good enough anymore to rely on a handful of cost-effective or least cost solutions. So I think, yeah, we were not expecting the system to have that much flexibility. Of course, the underlying transmission models have to be considered in a much better way, but just the possibility of that much flexibility in technology portfolio within your budget, we were completely blown away by it.
Yeah, I think another question that I always have that's kind of related when you think about least cost, like optimizing for least cost, is that, sort of least cost for who? And depending on how you're building out this energy transition, like we're not talking about everybody. The costs are not being paid by one entity. There are many different entities that are paying different costs.
Yes.
And there are also different ways of distributing the benefits. And so I think from that perspective, I'm just curious if your team is thinking about how to think about different ways to distribute costs and benefits that really might affect decision making, because yeah, it's not like there's one entity necessarily that's bearing the cost. So
Absolutely. Yeah.
maybe.
For sure. Right now, we are thinking from a system planner's perspective, right? And of course, there is no one system planner. You're absolutely right. And so one thing we are trying to do with this new project is that you can see when you take the capacity expansion results, downscale them, put it into the operational model, you can see the price curves at much more or much higher resolution, right? Right now we have, from the capacity expansion model, we have price profiles for each region. Instead of each region, there are 8 regions in New York right now. You can see that price projections for 62 different nodes spread across New York State. And you can see how wholesale electricity price would be affected, and would be that cost will be affected in different regions of New York. And that is also one of the objectives where you don't want the cost to negatively impact certain areas or a specific area. And we want to see whether a more equitable distribution of that cost is possible within your budget as well. Right. There are costs for transmission and distribution that, yeah, we cannot consider right now. But yeah, it's a very important.
Yeah. All right. Well, if we could again give Dr. Patankar a round of applause, at least virtually. And yeah, just want to say a big thank you. Really appreciated hearing about your work and learning from you. And yeah, well, hopefully we'll be in touch. And best of luck with your leave too.
Thank you so much.
All right. Take good care. Bye, everyone.